Gas laws. There are laws about the behavior of gases, and some of these things you already know. You just don't know them mathematically. Because most of you are drivers now, right? Some of you are drivers. But have you ever looked at a car tire on a really cold day? What's it look like? It looks softer, right? It's not quite as it doesn't have as much pressure. That's a direct application of the gas laws, right? Because there's a relationship between temperature and pressure. Right? So we're going to start with the pressure-volume relationship. The good news, you don't have to memorize who Boyle was. That's the part that when I was in high school, my teacher made us memorize the gas laws by people, and that was awful. At the end, I'm going to give you a way to derive every gas law. It'll take you like 15 seconds. You can get any gas law you want, even ones without names, which is kind of nice. I do refer to the textbook because the textbook, this is one thing the textbook does a great job on. So if you're interested in the textbook, please read pages 441 to 443. It looks like a lot. You're like, oh, 3 pages. No, it's like a page that you've got to read, maybe a page and a quarter. Most of it's diagrams and stuff. So read that. Review example problem 1. Example problem 1 is very similar to the example that I'm giving you. So let's look at it. First, we have to know what Boyle's law's equation is, and it is P1 V1 equals P2 V2. And the P's are pressures, and the V is volume. That's not too challenging, is it? Pressure and volume. And what this is saying is that if you have something at a particular pressure and volume, and you increase or decrease the pressure, the volume will change accordingly. If you increase the pressure, what will happen to the volume? If you squeeze something that's filled with gas, what will it do? It'll shrink. So the volume will get smaller. So if this goes up, the volume will go down. What kind of relationship is that? Well, if one went up and the other went up, that would be a direct, right? This is an inverse relationship. Okay. So as one gets larger, the other gets smaller. And underwater is one of the best examples of this. So a diver is underwater, 15 meters, it's about 50 feet, right? About 50 feet underwater, and he blows a bubble that's about a half a liter. As it rises to the surface, the pressure gets smaller. What happens to the bubble? Pressure. Yeah, the bubble expands. It gets bigger because the gases inside are expanding. Okay? That is Boyle's law, but we've got to do it mathematically. The pressure goes from 3.75 atmospheres, so that's just over 3.5 times the pressure that we are right now, to just short of 1 atmosphere. That's about the pressure we're at right now. Actually, we're closer to about 0.992, but that's, I mean, for measurement, it's really close. How big does the bubble get? What's the volume of the air? So what volume does the bubble start at? Yeah, 0.53 liters. Okay. So ones are where we're starting. What pressure are we starting at? What pressure? What was the pressure where the diver was? Yeah, just 3.75 atmospheres. Okay. And what is the pressure right there next to the surface? Well, we go back to the question and we see the pressure is 0.981 atmospheres. And that unknown is our V2. Well, this looks kind of familiar, right? Remember M1 V1 equals M2 V2? Let's do it the same way. Using Boyle's law, we solve only using the variables. So we have P1 V1 equals P2 V2. We got to solve for that V2. Just do a little algebra. Divide both sides by P2. And that gives us an equation. V2 equals P1 V1 over P2. I do this with variables, again, because most of us are better at moving letters around than numbers, because now all we have to do is substitute and solve. Because we have a P1, we have a V1, and a P2, we simply take V2, set it equal to 3.75 atmospheres, times 0.53 liters, and divide that whole thing by 0.981 atmospheres. Notice quickly about units. If I cancel any units that I cancel both of my atmospheres and I'm left with liters. So what's my answer going to be? Whatever it is, it's in liters. Then I grab my handy dandy pocket calculator. 3.75 times 0.53 and divide it by 0.981. And my answer is 2.0 liters. So a bubble from 50 feet down gets 4 times larger by the time it gets right next to the surface because of the relationship between the pressure and volume of a gas. Handle that one? Yeah, hopefully. So let's introduce Charles's law. So again, I refer to textbook pages if you want to review in the textbook. It's there for you. But I will go ahead and give you Charles' law's equation. It is V1 over T1 equals V2 over T2. Okay. I'm going to show you a quick video. And it has to do with what happens to the volume and temperature, or volume in a particular temperature. Let me reshare so that people online can see what's going on. These are fluid animals, and this is liquid nitrogen. So this is what, 20 Kelvin or so, 30 Kelvin. Really, really, really cold. What happens when they warm up? The temperature increases, the volume increases. I I do that, except for I don't have the specialized equipment for liquid nitrogen, and it's a little expensive. I'm working on it. So what kind of relationship is that? So the temperature decreases, the volume decreases. The temperature increases, the volume increases. We call that a direct relationship. Okay. So the dependent variable responds directly to the independent variable. If you want to test this at home, blow up a balloon, stick it in your freezer for a couple of hours, come back and look at it. Then take it out of the freezer and let it reach room temperature, and you will see the same kind of thing happen. It just takes longer because your freezer is not quite as cold, and it, liquid nitrogen, I mean, it makes things cold very, very quickly. You can make ice cream in about 4 seconds. Just really fun. Hurt your arm because you got to stir really quickly, otherwise it just freezes into a big block. So helium balloon in a closed car occupies a volume of 1.89 liters at 42 Celsius. That's hot. Okay. But it's going to get really hot in there. It's a summer day. You're in Arizona, and that temperature rises to 82.7 Celsius. And what's the new volume of the balloon? So where did we start? What was our starting temperature? We started at 42 Celsius, 42.0 degrees Celsius. And when we started there, our balloon was only 1.89 liters, right? And our final temperature was 82.7 degrees Celsius. But now we have a little hiccup because temperature is an issue. And the issue is we can't multiply or divide with Celsius temperatures. It's not an absolute scale. 0 in Celsius is not really 0, right? It can get colder. You can only multiply and divide with absolute numbers. So we've got to convert the Celsius to an absolute scale, and we're going to convert that to Kelvin. So to convert Celsius to Kelvin, we add 273 to the Celsius. So we take 42 plus 273, and this is 315 Kelvin. Okay. I'm going to take 82.7 plus 273, and that's going to make things 355.7 Kelvin. Because Kelvin is an absolute scale. 0 Kelvin means there is literally no heat, no movement. The molecules even stop vibrating. So that's an extra step. When we're doing gas laws, this is where probably 65% of the points are lost by students. You've got to make sure you convert everything to Kelvin, which is why later on, those of us who were in chemistry for longer, just make it a practice. If you see a Celsius temperature, we just convert it to Kelvin because no one marks it wrong if you would do that. So we're going to use Charles' law, and we've got to solve for the unknown using only variables. So we've got V1 over T1 equals V2 over T2. And we have to solve for that V2. This is when algebra sometimes gets a little twitchy for some people, right? How do we get V2 by itself? Multiply both sides by T2, which allows that to cancel. And we end up with V2 equals T2 V1 over T1. And again, now it's just substitute and solve. I say that more now. I taught my daughter, and she doesn't like it when people say plug and chug. All right, 42 V2 equals T2 is 355.7 Kelvin times V1, which is 1.89 liters, over T1, which is 315 Kelvin. Again, our Kelvin will cancel, treat our units like variables. That will make sure that you are solving for the right thing, because a volume should be in liters. That's good. 355.7 times 1.89 divided by 315. And our new volume, if I've done my math correctly, is 2.13 liters. It's all pretty doable. So we're going to have our 3 gas laws and convert to Kelvin, and everything is good. Because we have a third gas law, which is Gay-Lussac's law. And again, it references the pages in the book for you to look for if you want to go hunting there. Gay-Lussac's equation, though, is T1 over T1 equals P2 over T2. And those of us who drive and have to put air in our tires understand this gas law pretty well. Because on a hot day, our tires may have higher pressure, and on a very, very cold day during the winter, our pressure may drop so low that our little tire indicator may come on. Keep your eyes on it this winter if you're a driver. You see that, you can say, it's Gay-Lussac's law in effect. Because once again, this is a direct relationship. On the cold day, we have lower pressure, and on the hot day, as temperature increases, our pressure also increases. So the pressure of the oxygen gas inside a canister is 6 atmospheres at 23 degrees Celsius. We put the canister on Mount McKinley, high up, lower pressure. It's also colder there, and the temperature falls to -2 Celsius. What's the new pressure? So our pressure starts at 6 atmospheres. And it's at 23 degrees Celsius. And then we take it up on that mountain, and it gets cold to -2.00 degrees Celsius. And before we do any other calculating, we must convert to Kelvin. So 6 plus 273 is, 23 plus 273 is 296. Okay. And this is 271 Kelvin. We are looking for the new pressure, P2, so we need to then do a little algebra. P1 over T1 equals P2 over T2. And in this case, once again, we multiply both sides by T2, which gives us a final P2 being equal to T2 P1 over T1. And then it's simply a matter of substituting and solving again. So P2 equals T2, which is 271. And our P1, which is 6.00 atmospheres, divided by our T1, which is 296 Kelvin, and that gives us a grand total of 5.49. And again, our Kelvin will cancel, so our final unit will be atmospheres.
You accept like 5.5 or something like that?
No. 3 sig figs, 3 sig figs, 3 sig figs.
Oh, it's 6.00.
That's right. And the given above, which is why I copied it with the zeros, the given was 6.00.
Yeah, I just forgot to.
Yeah. No. That's it. There are 6 questions. That is the assignment for the day. You need to bind your paper. These 6 questions are based upon the 3 gas laws. Define your variables, figure out which gas law, solve for the unknown, and then substitute and solve. Make sure you convert to Kelvin if you have a temperature that's not already in Kelvin. You need help? I am here for you.
Is there a place to turn these ones in?
Say again?
Is there a place to turn these ones in?
Yep. There is, as of this morning.
That's not what I had. No,
Overtrained. Don't be afraid of the different units. You'll see things like PSI and KPA for pressure. Pressure is like 14 different units. The law holds true for all of them because they're all absolute scales. What's PSI stand for? Anyone?
pressure per square inch.
It's pounds, but yeah, pounds per square inch. KPA is the one people don't know because it's the actual SI unit. It's kilopascal. Because Pascal got to invent his unit, and guess what it was named? Yeah. Same thing as the pressure unit for not pressure. The force unit. Force unit is newtons. Pressure unit is pascals. Okay, good. Freeze that. Unsafe changes. Presence here. Sydney, Jacob, Ellie, Colin, Aria.